So in this section, we are going to learn a very important concept and very interesting concept of organic chemistry, that is SIP and SIR. Full form of SIP is steric inhibition of protonation. Let me write steric inhibition. Inhibition. Steric means steric hindrance or bulkiness. Inhibition means something type of restriction like that. Okay, inhibition of protonation. Protonation. And SIR means steric inhibition of resonance. That means something is prohibiting resonance and something is prohibiting protonation. And what is prohibiting them? Steric. That means steric hindrance at one case is prohibiting protonation. In another scenario, steric hindrance is prohibiting resonance. So let's get started. First one, let's discuss steric inhibition of resonance. That means the steric hindrance is restricting or prohibiting resonance. These things are very much common in describing the acidity of carboxylic acids and basicity of amines. First, let's take an example of carboxylic acid. For example, C double bond OOH, benzoic acid. Now, I am going to compare its acidity with orthomethyl benzoic acid, C double bond OOH, CH3. Now, if I want to compare the acidity between the two, here what happens? Methyl is a bulky group. Now, for the bulkiness of methyl, what will happen? This bond will rotate. If we want to discuss the acidity, we know more the acidity, more the stability of conjugate base, or vice versa. So let's draw its conjugate base. For example, this one, C double bond O minus, it will be conjugate base. For this structure, conjugate base will be C double bond O minus, and methyl. Now, what will happen? This methyl is a bulky group, and for this group, for this bulkiness, this single bond will rotate, because if they are in plane, if C double bond O and the benzene ring all are in plane, then O minus can undergo resonance with this benzene ring. Try to understand it in a different way. For example, it is our benzene ring, and there is C double bond O minus. All things are in plane. Everything is in plane. That's why this lone pair, this pi electron, this pi cloud, these p orbitals, and these p orbitals are parallel to each other. That's why there is a fine conjugation possible, like this. This complete conjugation of the ring with that O minus, complete conjugation is possible. But if we put one bulky group here, what will happen? This bulky group will generate steric hindrance with this group, and when the group will not able to bear this steric hindrance, what will happen? This bond will migrate, and the whole C double bond O will be shifted like this, will be tilted like this. Okay. Now what will happen? Uh, the resultant structure will be now CO minus double bond O. Now it is in different plane, and this is the group. Now this p orbital is in this direction, but in benzene ring p orbital is in this direction. So there will be no resonance, right? So this is basically steric inhibition of resonance. Why? This group is inserting the steric hindrance into this system, and for this steric hindrance, when the C double bond OO is perpendicular to this ring, then C double bond OO will not able to undergo resonance with this extended benzene ring. So the extended conjugation of C double bond OO is broken by this methyl group steric hindrance. That's why it is steric inhibition of resonance. So steric hindrance of methyl is inhibiting the resonance of C double bond OO or C double bond OO minus with this benzene ring. This resonance is getting inhibited by this methyl group. That's why it is steric inhibition of resonance. Now what will happen? What will be the result? For this simple benzoic acid anion, what will happen? The resonance will happen throughout the ring. So in the resonating structures, if we draw all the possible resonating structure, we will be getting that. For example, it will be one resonating structure. For example, this will be another resonating structure. For example, this will be another resonating structure. So there will be so many resonating structures where carbon will be involved, where oxygen will be involved. Okay, but so here total we will get 5 6 resonating structure. We will get 1 2 3 4 5, mainly 5 or 6 resonating structure we will get. And somewhere in some resonating structure charge will be on oxygen, in some resonating structure charge will be on carbon, right? Now if methyl group is acting as a steric inhibitor, then what will happen? This C double bond OO resonance will not be able to continue with this benzene ring. So for this structure, only two resonating structure is possible. One is this, another one is this one. So this C double bond OO will not able to undergo resonance with this whole ring. So one resonating structure will be C double bond O minus, and another resonating structure will be CO minus double bond O. For orthomethyl benzoic acid, we will have only two resonating structure. But for this, we will be having 5 6 resonating structure. And we all know if more resonating structure, more stable the system is. You know, right? But there is a fallacy. What is that? We know another rule that when we compare resonating structure stability, we know that similar kind of resonating structure, similar type of resonating structure contribute more, right? That's why a very popular question is there. Guanidine, guanidine act as a very strong base. Why? The explanation of the question is the similar kind of resonating structure, similar type of resonating structure. Here, obviously, we will be getting 5 6 resonating structure, but all are not similar kind of. Some are having charge on carbon, some of are having charge on positive. Okay, so there are versatile different kind of resonating structure, but here only two resonating structure and contribution will be 50-50, isn't it? Because both are actually similar kind of structure. So overall, this system is very much stable. Okay, so conjugate base of orthomethyl benzoic acid is very much stable. So that's why it is a stronger base. So with this concept, if we compare acidity of, for example, COOH ortho, COOH meta, and COOH para, what will happen? What will be the acidity order? We know that the steric inhibition of resonance for this compound, steric inhibition resonance is also called ortho effect. Okay, ortho effect. Okay, because in ortho position this phenomenon is possible. In meta position, this is far away. This phenomenon is not possible. So ortho will be more stable. So 1 will be more stable, and then 2, then 3. Why 3 will be least stable? Let's see. In 3, let's make conjugate base C double bond O minus, this, and CH3. We know this CH3 will show hyperconjugation. For showing hyperconjugation, what this will do? Hyperconjugation occurs in this way. right? So for CH3 hyperconjugation from para position, this O minus resonance with this double bond O will be hindered, or will be you can say will be repelled. Okay, for this conjugation, OH minus will not able to donate its electron to that oxygen, so this resonance will be hampered. That's why conjugate base stability will be dropped. That's why acidity will be lowest for para methyl benzoic acid. So this is basically ortho effect and steric hindrance of resonance. In the next section of discussion, we will be discussing uh, the extension of steric inhibition resonance in amine, and with that segment I will be discussing the steric inhibition of protonation also, because in amine both the concept steric inhibition of protonation and steric inhibition of resonance both applies. So in next segment we will be first discussing steric inhibition of protonation, then we will be connecting steric inhibition of resonance and steric inhibition of protonation in describing the basicity of um, amines, different kind of amines. And there will be students get confused there in so much, because primary amine, secondary amine, tertiary amine, aromatic amine, all their different concept, these two concept mixes, and they are actually oppositely affect the acidity or basicity of those compounds. Okay, so we are going to discuss in the last segment.